Hello everyone, welcome to another video lesson in linear algebra. This lesson covers the determinant of an n by n matrix. As a quick motivation, determinants are simply scalars which determine whether a given matrix is non-singular or not. You know how important non-singular matrices are in linear algebra, right? But in order to properly define determinants, we need the following concepts. The concept of permutations is required to be able to have a proper definition for the word determinant. Informally, you have seen permutations on a set as an arrangement of all the elements in a row. For example, if three children are, let's say, posing for a picture and they are going to be arranged in a row, then these three children can be arranged in different ways. For example, they are labeled as child 1, 2, and 3. These three children admits six distinct permutations as follows. So they can be seated as 1, 2, 3, or they can be seated as 2, 1, 3. They can be seated as 3, 1, 2, or even 1, 3, 2, or 3, 2, 1, or 2, 1, 3. Take note that these three children can be arranged in six different ways if they are going to be seated in a row. And these are all the six ways to arrange them in a row. Each one of these is called a permutation on the set X, which has elements 1, 2, and 3. However, in mathematics, the word arrangement is not really a well defined term. To be able to come up with a proper definition, we will be using the concept of bijections, which are one-to-one and onto functions from a set to itself. All right, so a permutation on a set X consisting of the elements 1, 2, 3, 4, and so on up to n. So basically, X is a finite set. No? So a permutation on X is simply a bijection or a one-to-one function from X onto itself. The set of all permutations on X is denoted by S sub n. So meaning to say, all the functions that you can construct from X to X, which will be both one-to-one and onto, are considered permutations on X, and the set of permutations is denoted by S sub n. Again, when we speak of a permutation on the set X, we only mean a one-to-one function from X onto itself. We can think of a permutation pi, for example, in S sub n as a manner of assigning n distinct applicants to n distinct jobs so that each applicant gets exactly one job. For example, if you look at the permutation 1, 3, 2, for example, you can think of this as a function, no? A function, by the way, assigning 1 to 1, 2 to 3, and 3 to 2. The elements listed here are the images arranged in a particular order depending on the order of 1, 2, 3. For example, 1 is the image of 1, 3 is the image of 2, and 2 is going to be the image of 3. As a job assignment, you can think of this as applicant number 1 gets assigned to job number 1. Applicant number 2 gets assigned to job number 3. Applicant number 3 gets assigned to job number 2. As a matter of fact, if pi is an arbitrary permutation on S sub n, we oftentimes define or denote pi by simply listing down the images starting from the image of 1 then the image of 2, the image of 3, and so on, up to the image of n, arranged in this manner. For example, when we write down the permutation pi, denoted by 3, 1, 2, so this means that 3 is the image of 1 is the image of 2, and 2 is the image of 3 under the function pi. You can somehow represent it using a diagram by putting an arrow, no, from 1 going to 3, because 1 gets assigned to 3, 2 gets assigned to 1, so we are putting an arrow from 2 to 1, and 3 gets assigned to 2, so we are putting an arrow from 3 to 2. This time, think of it as if applicant number 1 gets assigned to job number 3. Applicant number 2 gets assigned to job number 1, and applicant number 3 gets assigned to job number 2. Take note that this is really a permutation because each applicant gets exactly one job. We now ask, given a positive integer n, how many permutations are there on the set 1, 2, 3, and so on up to n. So, if there are n applicants and n jobs available for these applicants, it is asking as if how many ways to assign these n applicants to these n jobs so that each applicant gets exactly one job. So, if you think of these blanks as the job numbers, no? This is job number 1, job number 2, job number 3, job number n. In the first position, without any restrictions at all, we can assign n different applicants, or there are exactly n ways to assign an applicant to job number 1 as none of the applicants is already assigned. In the second position, knowing that an applicant has been selected on the first position, in the second position there will only be n minus 1 possible choices. For the third job, we can assign n minus 2 because 2 applicants has already been assigned, and so on, up to the last position where we only get one choice. So by the fundamental counting principle, there will be a total of n times n minus 1 times n minus 2, and so on, times 2 times 1. Number of ways you can assign these n applicants to n jobs. So therefore, this is shortened as follows. Hence, the number of permutations on the set X with n distinct elements, no, is equal to n factorial. Now, given a permutation in S of n, a permutation can perform an inversion. So, an inversion is defined technically as follows. Pi is said to perform an inversion if there exists an ordered pair R and S, each of R and S are integers from 1 to n, no, such that R is less than S, but pi of R, but the image of R under pi is greater than the image of R under pi. So, how do we think of inversion? So, now, assume that these are the list of applicants and these are the list of jobs. Now, we use the symbols 1 to n, no, because they denote a particular order. So when we say, no, let's say these are the applicants and these are the jobs. Okay. So let's put a particular order on the applicants. So the bigger, let's assume that the bigger the applicant number is, it means the bigger or the better the credentials. For example, 3 has a better credential than 2, 2 has a better credential than 1, and so on. So in that particular order. Now let's say these numbers representing the jobs denote the, let's say, the position or the hierarchy in the company. So for example, 3 is the, let's say, the highest paying job, because it's of the highest rank, then followed by 2 and by 1. An inversion is just a pair of applicants. No? For example, if you look at the previous example, the permutation pi, which is, what is that again? 3, 1, 2. So it's represented using the following arrow: 3, 1, 2. As you can see, no, applicant number 2 has a better credential than applicant number 1. But as you can see, applicant number 1 gets the job with the highest position than applicant number 2. That is considered an inversion. For example, the ordered pair 1, 2 is an inversion because 1 is less than 2, but the job assigned to applicant number 1, which is 3, uh, is bigger than 1, which is the job assigned to applicant number 2. So that's what we mean by an inversion. Let's consider a bigger example. For example, pi is 15324, and this is in S of 5 because there are now 5 applicants and 5 jobs. This permutation performs the following inversions. For example, 2, 3. Why? The image of 2 is 5. The image of 3 is 3. As you can see, even though 2 is less than 3, the image of 2 is bigger than the image of 3. Also, 2, 4 is an inversion. How do we say so? Because 2 is less than 4, but the image of 2 is 5, and that's greater than 2, which is the image of 4. Okay? 2, 5 is also an inversion, as well as 3, 4. Remember that you can always pause and rewind if you find that the discussion is quite fast. In this particular example, one can verify that these are the only inversions the permutation pi performs. To quickly identify the inversions in the permutation 1, 5, 3, 2, 4, what we do is we look for a pair of integers in the list so that um, going from left to right, no, if you see something, for example, when you look at 2, 3, when you look at 2, 3, this 2, 3 represents the second and the third position. Because the second position has a bigger image than the third position, that is considered an inversion. So this is an inversion. Whenever you see a bigger element on the left of a smaller element, that is an inversion. Okay? For example, 2, 4 is also an inversion because the image of 2 is 5, the image of 4 is 2. And that can be represented by this line, no, or this curved line, because 5 is greater than 2 and 5 is positioned to the left of 2. That is considered an inversion. Also, 2 comma 5 is an inversion because the image of 2 is 5, the image of 5 is 4. So these are the two elements. And as you can see, 5 is positioned to the left of 4. Last but not the least, this is also an inversion because 3 is positioned to the left of 2. Take note, for example, that this is not an inversion because that's just okay, no? 3 is on the left of 4, 3 is less than 4, that's fine. So if you're going to count the number of inversion this permutation performs, it's just the number of arcs that we have drawn. So in this case, there are 4. If you're going to count the number of inversions a permutation performs, that is either even or odd. So we will say that a permutation is even if it performs an even number of inversions. Otherwise, we will call it as odd. So in the case of this example, the permutation pi is even because it performs 4 distinct inversions, which is even. For example, the permutation 1, 2, 3, 4, and so on up to n is called the identity permutation because it sends 1 to 1, 2 to 2, 3 to 3, 4 to 4, and so on, n to n. This is always even as it performs no inversion at all. It performs zero inversion, and we know that zero is even. It turned out that in S sub n, the set of odd permutations is has the same number as the set of even permutations. This is not easy to see, but it can be proven. For example, in S sub 3, if you look at S sub 3, these are the 6 different permutations. No? So let's count the number of inversion each one performs. For example, this has 0 inversions, no? Because this is the identity permutation. This permutation 1, 3, 2 performs only 1. So by the way, this is even. This one performs only 1, so this is odd. 2, 1, 3 performs what? 1, right? 1 inversion. Therefore, this is odd. I think there's a repetition over here. I'm sorry. What is missing? Yeah. I'm so sorry. As you can see, this permutation 213 is the same as this. I'm so sorry. I think this one is 231. 231 is missing. All right. So in this case, 231 has two inversions, so therefore this is even. 312, one inversion, two inversion, so that's again even. 321, 1, 2, and then 3. So there are 3 inversions, so that is odd. 213 as well, 1 inversion only, so therefore this is odd. As you can see in S sub 3, there are 3 even permutations and 3 odd permutations. Actually, the proof of this fact can be done in abstract algebra in a more in a more rigorous look at permutations on a finite set, and we will not be proving this fact anymore. No, in our case, you can just look at your notes in abstract algebra and find that the set of even permutations in S sub n equals the number of odd permutations in S sub n. This is also one important what do you call this property of permutations. If two elements in a list representing the permutation is switched, then the parity of the permutation, and say parity, the evenness or the oddness, gets changed. Meaning to say, if your permutation is originally even, you switch two elements from it, then it will be odd. But vice versa. If your permutation is odd, you switch two elements, it will become even. Let me just illustrate a particular example. So you have 5, 1, 3, 4, 2. So to count the number of inversions, you look for bigger elements found in the left of to the left of a smaller element. So for example, 5 is the biggest, so anything on the right, on its right, is an inversion. Determines an inversion. This is also an inversion because 4 is bigger than 2, yet it's on the left of 2. Oh my god, I missed this one. That is also an inversion because 3 is greater than 2 and it's placed the left of 2. Any other inversions? I don't think there's more. Right? So, all in all, how many permutations does this perform? One inversion, rather. 1, 2, 3, 4, 5, 6. So this permutation is even. Now let's consider the permutation sigma obtained by switching two elements from pi. Let's say I switch 2 and 5. 2, 1, 3, 4, 5. This is now a different permutations, right? If you count the number of inversions, these are it's going to be 2, 1. What else? No more. Only 2, 1 is there now as an inversion. As you can see, sigma is odd because two elements in the permutation are switched. This can also be proven in abstract algebra, and we don't have enough tools to guarantee this. Now, there is some sort of notation that we are going to use. No, if pi is a permutation in S of n, it's either even or odd. No? If it is even, we will write or we will uh, mean 1 for the expression minus 1 raised to pi. No? It's like raising negative 1 to an even integer, therefore it's 1. No? But it's not really an integer. No? Pi is a permutation. So if pi is odd, we shall define this expression as negative 1 instead. Okay? So I think we are now ready to define determinants. If you have an n by n matrix A with entries aij on the ij position, its determinant is defined as this particular scalar. It's either denoted by that A or the matrix A, which are where we put a pair of vertical bars around A, now to denote that we're taking the determinant of A. So either of these annotations can be used. As you can see, the definition is quite, what do you call this? It's quite complicated at first look, but it's not really um, hard to understand. First of all, how many terms are there in the sum? As you can see, the sum is taken over all permutations pi in S sub n. So in other words, each permutation in S sub n gives us one particular term in the summation. Because S sub n has n factorial terms, therefore, this summation or this determinant has n factorial terms in it. Now, how about the terms of um, the determinant? How can we describe them? If you look at these A's, no, as you can see, this A is found on the first row because of the subscript 1. This A is found on the second row. And this A is found on the nth row. And the column numbers, as you can see, depends on how we select the permutation pi in S of n. So let's not look at the column numbers. Let's just look at the row numbers first. So if you look at the row numbers, it's as if we're selecting one element from each row in such a way that the column numbers are the images of the row numbers under a certain permutation. So because this is a permutation, meaning to say, this will never repeat objects. So meaning to say, we're simply getting an element from each row while we select them in a way that they don't repeat column numbers. Alright, so that's what we mean by each term. Now, the sign of the term will be determined whether pi is even or odd. Now, if it's even, by the way, this is a positive 1. If pi is odd, this is going to be a negative 1. This is why every term of the determinant is a signed product of n entries obtained by taking one entry from each row, such that no two entries are in the same column, as every term is determined by every column number is determined by a permutation in S sub n. Signed, it's either plus or minus, depending on whether the permutation that you have selected is even or odd. And of course, there's no better way to um, explain this definition but by looking at certain examples. By the way, if A is 1 by 1, no, its determinant is just the 1 by 1 and 1 entry. No, nothing more than that. That's a trivial case. So let's move on to a 2 by 2 case. So if A is now 2 by 2, these are the entries of A. What is the determinant of A? To have the determinant of A, we first look at S sub 2. S sub 2 has two elements, namely the permutations 1, 2, and 2, 1. Okay? So you can see 1, 2 is even because it performs no inversions. 2, 1 is odd because it performs one inversion. So the even permutations are labeled blue. The odd permutations is labeled red. When you look at the determinant of A or the determinant expansion of A, see that it has two terms because we have two permutation here. Now, the row numbers will always go from 1 to n. So just like this, 1, 2, 1, 2. The column numbers will depend on which permutations that you are selecting. For example, if you select the permutation 1, 2 for the first term, it's going to be A11, A22. This is the permutation 1, 2. Because this is even, this is of positive sign. Then 2, 1, because 2, 1 is odd, this is going to be of negative sign. You understand? There are two terms because there are two permutations in S sub 2, 2 factorial. You can illustrate, or as a mnemonic device, you can illustrate a 2 by 2 determinant using the following. No? A11 times A22 represents the product of the main diagonal entries minus the product of the anti-diagonal entries, A12 times A21. As an example, if you have this 2 by 2 determinant, it is equal to 2 times 4 minus negative 3 times 1. And that's 8 plus 3, that's 11. So the determinant is 11. So for a 2 by 2 matrix, that's kind of easy, right? Let's look at a 3 by 3 example. If you have this 3 by 3 example, how many permutations are there in S of 3? There are 6. I have listed down here the 6 permutations where the blue ones are the evens and the red ones are the odd. So the determinant of A, the expansion consists of 6 terms. 3 of it has plus sign, 3 of it has minus sign. The first term should be the one using 1, 2, 3. Okay? The second term should be the one using 2, 3, 1. The third term should be the one using 3, 1, 2. The fourth term should be the one using 1, 3, 2. Take note that we now have a minus sign. The fifth term is the one using 3, 2, 1, which uses minus sign. The last one uses 2, 1, 3, which uses a minus sign because it's odd. So you see that this determinant has 6 terms. Now, how can we remember this formula? Now, we use the following mnemonics for the 3 by 3 case. We first repeat the first and the second column and attach it to the right of the given matrix. So this is the first column repeated, second column repeated. Once we have done repeating that, we do the following down arrows. The down arrows represents the 3 plus terms. And then we subtract the product of the entries in the up arrows. No? So these are the 6 different terms in the determinant. We multiply the entries in each arrow and then add them. For the red ones, we subtract them. Okay? This method is sometimes called as the basket weave method. Anyway, so for example, let's evaluate the following determinant. So the first step, because this is a 3 by 3, we simply repeat the first row and the first column and the second column as follows. And then Follow this pattern. Okay, the down arrows, the product of the entries in the down arrows represents a positive one. So what I do is I simply list them down. 2 times 2 times 4 is 16. Minus 3 times minus 1 times 3, that's not positive 9, right? And then 5 times 1 times negative 1 is a negative 5. For the up arrows, I'm going to use these red ones, all right? And then I'm going to collect all the negative terms and just place them outside a parenthesis. So I'm going to add inside the parenthesis. So 3 times 2 times 5, that's 30, I guess. Plus minus 1 times 2, that's 2. Plus 4 times 1 times negative 3, that's negative 12. Is that correct? So this is now 25 minus 5, that's 20, minus 32 plus negative 12. I think that's 20 as well. Hmm? Yeah, 20 as well. Oh, so the determinant is actually 0, right? You can pause and rewind if you want. Now, warning! Just a little bit of warning. The basket weave method only works for size up to 3 by 3. No? Yung up arrows, down arrows. For the 4 by 4 case and above, no, we stick with the definition. Kasi if you have a 4 by 4 matrix, for example, there are only 4 down arrows and 4 up arrows. So there will only be a total of 8 terms. But in reality, n factorial or 4 factorial is 24. So you're missing out 16 possible, uh, 16, a total of 16 terms all in all when you just use the basket weave method. And of course, the determinant that you're going to get is something wrong. But that doesn't mean that we cannot really compute determinants easily for some good examples. This is one good example of a 5 by 5 matrix, and as you can observe, many of the terms are zeros. So remember that in order to get the terms of the determinant, we simply get the combinations of rows and columns. We pick one element from each row, for example, this one, so that you're not repeating columns while doing a picking from each row. Do you understand? Of course, to have a non-zero term, we should pick something non-zero from every row. So you can see for the first 4 rows, only one entries are is non-zero. For example, for the first row, we only have 1, second row 2, 3, third row 3, fourth row 4. But on the last row, everything is non-zero. So how do we get to select our term, or how do we compute this determinant? As you can see, all other terms are 0 except for this. So you can have 1 for the first row, 2 for the second row, 3 for the third row, 4 time for the third row. But which one should you pick for the last row? Can you pick can you just pick any other element? No, we can't, because we cannot repeat columns. So you take note of the column numbers of 1, 2, 3, and 4. So for example, this is 1. 1 is on the second row, 2 is on the fifth column. Sorry. 1 is on the second column, 2 is in the fifth column, 3 is in the first column, 4 is in the fourth column. So the only column not mentioned yet is the third column, which only has 7. So the only choice for the entry in the fifth row is the one in the third column. So that's going to be 7. But by doing so, you have to consider the permutation that determines the column number, because that's going to tell us what? That's going to tell us the sign of this term, the only non-zero term, right? What is the sign of this non-zero term? The permutation here lists down the column numbers in order you have selected. So for example, 1 is in the second column, so 2. 2 is in the last column, which is 5. 3 is in the first column, so 4. 1. 4 is on the fourth column, that's a 4. And 7 is in the third column, so this is the 5. If you look at the oddness or evenness of this permutation, let's count the inversions. 1, 2, 3, 4, 5. So there are 5 inversions all in all. So this is odd. Therefore, this is a minus 1. Okay? So all in all, the product is, what's that? I think this is negative 168. Negative. Okay? Are there other non-zero terms? No more. Now, by the way, let's put this down here. All right. The correct answer is negative 168, if that makes sense. The following are direct consequences of the definition. If A is upper triangular or lower triangular, so when you look at an upper triangular matrix, so you get something like this: A11, A22, let's say 3 by 3. Something here, something here, something here, and then all here are zeros. This is an upper triangular. As you can see, the only term possible here, no, or the only possible non-zero term is to get everything from the main diagonal. Aside from doing this, now for example, if you get this and then this, the only choice for the element in the third row is this one, so that term is 0. So the only surviving term is the one obtained by multiplying the main diagonal entries. But when you look at the column numbers of this represents the identity permutation 1, 2, 3. That's even. This is why, if your matrix is upper triangular, the determinant is simply the product of the diagonal entries. Also, when A is lower triangular, the same thing holds. In particular, because the identity is diagonal, which is also upper triangular, the determinant is just the product of the main diagonal entries, which is just 1, because the main diagonal entries are all 1s. And also, the determinant of the 0 n by n matrix is 0. Also, because when a matrix has a 0 row or a 0 column, the determinant is 0 because you always have to eventually get an entry from that row or from that column. So we are now going to list down some properties of determinants that we are going to use to calculate determinants efficiently. First, notice that when you take the transpose of a matrix, you're simply swapping the rows of the rows and the columns. So you can see getting an element from each row while not repeating a column is the same as getting an element from each column without repeating a row. Therefore, it is natural for the determinant of the transpose of A to be equal to that of A. For a more technical proof, no, if you have A with entries Aij, let's say the transpose is Bij, so by definition, Bij is equal to Aj for all I and for all j because we're swapping the rows and the columns. So the determinant of the transpose is equal to the following sum using the definition. Now take note that we are now using the b's because they are the transpose. Because this come from the transpose, because Bij is equal to Aj, we can turn this all into a's now. But then we have to swap the row numbers and the column numbers, right? But when you consider a particular permutation, pi of 1, pi of 2, pi of n, these are just 1 to n in some particular order. because but because number multiplication is just commutative, we can rearrange these terms again so that the first one to appear here is the one with 1 as the row number, no? So somewhere here is the 1, no, ilalagay mo lang siya dito. 2, lalagay mo na siya, ay dito ilalagay mo yung may 2 sa row number, I'm sorry. Kahit ako nalilito. Kasi kung ano man yung may pi of alin man diyan yung may n, lalagay mo yun sa last row. Okay? Well, to properly say that, take note that if you have a permutation pi in S of n, you can find a permutation that sends pi of I back to I. This is the one that will change. So that this is the one that I'm telling you. No? If you try to rearrange the term so that the row numbers appear in the natural order, the column numbers will be swapped, no? Or will be rearranged, and that rearrangement or that permutation is represented by sigma, okay, in some fashion. Therefore, the determinant of A transpose is equal to this, and that's the same as the determinant of A because you're simply getting all the permutations in S of n once again. But again, if you cannot understand the proof, the technical part of the proof, you just think of it as if whenever you're getting one from each row without repeating a column is the same as you're getting one from each column without repeating a row. This is why um, the determinant of the transpose is equal to the determinant of A. This is why when we have a theorem about determinants that involves rows, that theorem also holds when you replace the word rows by columns because the determinant of A and the determinant of A transpose are the same. For example, you can verify, no, as an exercise that these two determinants are the same. I don't know the exact value, but yeah, I think I did the computation here. So the 0 came from here. The 1 came from here. So 1 times 1 times 1. Negative 6 came from this. So that's 3 minus 2 times 1. The 0 came from here. The 2 came from here. 1, 1, 2. Negative 2 came from 1, negative 2, 1. So the determinant is 5. So you can also check that this has a determinant 5 if you wish. So this is what I'm telling you when it comes to determinants. Theorem involving rows are still true when rows are replaced by columns. Because the next thing that we're going to do is we're going to look at the effect of the elementary row operations on the determinant of a given matrix. Meaning to say, you have an original matrix, we look at what happens to the determinant when we perform either a type 1 row interchange, type 2 multiplying a row by a scalar, type 3 you add one row to a multiple of another. Now, these are the three elementary row operations. We will see the effect that they are going to do in the determinant of A. The first one being the row interchange operation. So, if a matrix B is obtained from a square matrix A by interchanging two distinct rows, then the determinant of that matrix will be of the opposite sign of the determinant of the original matrix. And again, this theorem holds even when you replace rows by columns. So when you swap two columns as well, the sign of the determinant will be changed. Did you understand? The reason for this is that when you interchange two rows from a matrix, the permutation involving the permutation that define the column numbers, no, two elements of that are being swapped. In effect, when you swap two elements in a permutation, the evenness or the oddness of the permutation changes. Therefore, every term of the determinant of B is just a negative of a term in the determinant of A. And this is why the sign of the determinant changes. Now, to have a good look of this property, let's look at this matrix of determinant. Of course, you can always proceed as usual. The down arrows and the up arrows, because this is just a 3 by 3 matrix. But if you look at this trick, now if you're going to use this property, for example, I could, for example, swap the first two rows. I don't know. What did I do? I swapped the first and the last row. Column pala, by the way. I swapped this, and what did I do? No, 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 no. I swapped the rows. I'm so sorry. First row and the third row. I swapped them. So I get the following. But take note that the sign will have to change. So that's the same as multiplying a negative 1 to the determinant. Right? So I'm swapping the first and the third row. Next, I'm going to swap the first column and the second column. No? Ito yun, no? They're swapped, so that produces the following, and then another negative 1 comes out. But two negative 1s in terms of multiplication is just 1. As you can see, it's just the determinant of this upper triangular matrix. I was able to convert the original matrix into an upper triangular one by just simply swapping rows and columns. Therefore, the determinant should be just the what they call this? The product of the main diagonal entries, which is negative 18. And this is basically the reason why we wanted to know the effect of the elementary row operations on the determinants of the matrix, because eventually, if you have a general matrix, not necessarily 3 by 3, we wanted, remember that we can always transform it into a matrix in upper triangular form or even lower triangular form if you want, by simply performing a sequence of elementary row operations. So if we can record the effects of these elementary row operations to the original determinant, then you can somehow track the determinant of the original matrix. That's the idea. So if a square matrix A has two identical rows or two identical columns, then the determinant of A is 0. So this is a corollary. When you say corollary, it's an immediate consequence of the previous theorem. So imagine that you have a matrix with two equal rows. For example, I have 1, 2, 3, 4, 5, 6, and then again I have a 1, 2, 3 over here. Why do you think the determinant is 0? For example, let's call the determinant as D. Right? So what I'm going to do is I'm going to swap the first and the third row, or the rows that are the same. If I do that, I get a determinant of minus D, right? But as you can see, nothing has changed really in the matrix because you just simply swap two identical rows. So therefore, the determinants are the same, so D is just minus D. That's 2D equals 0, therefore D is 0. So I think that's the proof. So again, just like as I've commented, to do the proof, you simply interchange the identical rows, changing the sign, but did not change the determinant at all. And that can happen only when the determinant is 0. For example, what is this determinant? Oh my gosh, this is a 6 by 6 determinant. Of course, we don't have time in the classroom. No? For example, when you're working in an exam, you don't have time. 6 factorial is very big. I think this is 720. So you cannot just look at the 720 combinations of the rows and the columns. No one does that. So wag kayong atake ng atake. So first observe the given matrix. Here, as you can see, the first column and the fifth column are identical. So even though the matrix is big, we know already that the determinant is equal to 0. So let's now look at the effect of a type 2 elementary row operation on the determinant. So if you multiply a row, or a column for that matter, by a scalar c, the resulting determinant will be also multiplied by c. So isang row lang ang i-multiply mo by c, the whole determinant gets multiplied to c. You know the reason for this? Because if you try to multiply a row by c, for example, remember that every term has to get, let's say, row I gets multiplied to c. Yan. But the determinant of the new matrix has to get an entry or has to get a factor from that row I. Therefore, every term will have an extra factor of c. Therefore, the determinant will have an extra factor of c. Okay? So let's look at this crazy example. This is a 3 by 3 matrix, but no one wants to do the basket weave method because these numbers are quite big. So again, if I ask you to do something like this without using a calculator, so think, or you have to maybe observe the matrix first. There is something maybe that you can do, or there may be a trick that you can do to evaluate this nicely. So, if you're going to observe carefully, you see that the, what do you call this? The third row is actually negative 2 times the first row. So in other words, each entry from the third row has an extra factor of negative 2. And according to the theorem, that's just negative 2 times the following. But the resulting determinant over here of a matrix, the matrix involved has identical first row and third row. So again, that's negative 2 times 0. Still, the determinant is 0. Okay? As a corollary, if you multiply a matrix, entire matrix by C, because this matrix has n different rows, each row gets multiplied to C. So if you apply the theorem n times to each of the rows now, then you have an extra factor of C to the n. Okay? Next, if you do a type 3 operation, what's type 3? You add a row to a multiple of another. If a square matrix B was obtained from A by performing a type 3 operation, row operation, or column operation if you want. Oh, so in this case, nothing will happen to the determinant. So of the 3 elementary row operations, this is the most complicated ones, di ba? And we use this to eliminate entries. But it turned out that nothing will really happen to the determinant when you do eliminations by type 3 operation. The determinant will be the same. To give you an idea why this is the same, in the module, the technical proof is included, but I will just show you um, a quick explanation why the determinant is unchanged. Now, let me do this for you. Suppose that A is this matrix and we perform the type 3 operation E31 parenthesis 3. So we are replacing the third row by the sum of the third row plus 3 times the first row. So B has the following form. No, I intentionally did not simplify the expression on the third row because I wanted you to see what really happens. So this is the determinant of B. Okay? Now in the determinant, take note that you have to get an entry from the third row every time. Yung 6 terms mo will always get an entry from the third row. Right? But each factor coming from the third row has 2 terms. So you can imagine like you have something like A times B times a sum of C plus D. Take note that this reduces to A times B times C plus A times B times D. So the original determinant gets split into two determinants, right? The first determinant uses only the first term. The second determinant uses the what? The second terms. Okay. So I want you to pause and think about this. Why this has to be true. Don't need to compute by hand now. You just think about it from the definition. Why is this true? Again, the reason because the third factor from each term has two terms. So the whole sum will have an extra term. Yung extra terms na yun will uh, comprise of this determinant. Okay? So, as you can see over here, this one is the original determinant of A. And the second one has an extra factor of 3. So that's that A plus 3 times this. But as you can see, what remains here, because you're using the first row as the pivot, no? The first and the third row actually is 0. So the 3 here doesn't does nothing to the original determinant because it will be multiplied by 0. This determinant is 0 because it has equal first and third rows. So no matter what that scalar is, this is just going to be 0. So the original determinant is the same as the new determinant. Okay? The fact that the determinant of In is 1 and each elementary matrix, do you remember the elementary matrices? Elementary matrices came from the identity matrix by performing the what do you call this? The corresponding elementary row operation. So the determinant of the elementary matrix Eij, this is obtained by switching two rows of the identity, the ith row and the jth row. We do that if the determinant of In is 1, so the resulting determinant of the elementary matrix Eij is negative 1. If you now multiply the ith row by lambda, now take note that we cannot multiply by 0 because the original of the determinant is 1. Now what happens to the determinant of a type 2 elementary row operation, elementary matrix? The identity gets multiplied to lambda on the ith row, so the new determinant will be lambda times 1 or lambda. And for the type 3 matrix, again, this is not 0. The determinant of the type 3 matrix is also 1 because the determinant will not be changed when you do a type 3 operation. Okay? So one can observe that the determinant of any elementary matrix is not 0, is non-zero. That is, if E is an elementary matrix, then the determinant of E cannot be 0. As a corollary to this, we have the following. If E is an elementary matrix and A is an n by n, then the determinant of E times A is equal to the determinant of E times the determinant of A. Why is that? Remember, EA is the product EA, no, is the same as the matrix obtained from A by doing the elementary row operation corresponding to this elementary matrix. So for example, if I do what do you call this? If I do a type 1 element, if E is a type 1 elementary row operation, elementary matrix, so EA will just be obtained from A by switching two rows from A. So the left hand side is equal to det A times negative 1. On the other hand, the right side, ang determinant ng type 1 matrix ay negative 1. So this is negative 1 times det A. As you can see, the equation holds. If E is of type 2, EA will be, if you multiply lambda on the ith row of A, so that will be lambda times det A. Yung right-hand side mo naman, this is lambda, that is that A, so equal all the time. Pag type 3, syempre walang mangyayari, 1 lang ito at ito magiging that A lang din. Di ba? So in any of the cases, the determinant of EA is equal to that E times that A whenever E is an elementary matrix. As an immediate corollary to this also, if you have many elementary row operations over here, let's say the EIs are elementary row operations like this, elementary matrices. This can be written as that E1 times that E2 and so on, that EK times that A. This can be done by applying this corollary many times. So you will see why. Okay? So we have now come to, after 1 hour of studying, we have now proven the following theorem. This is the main theorem of this lesson. Why determinants are called determinants? Because they determine whether a given matrix is non-singular or not. So if you have an n by n matrix, then it is non-singular, it is invertible, no? If and only if the determinant is not zero. So to those cases where we get a zero determinant, the given matrix is singular. Whenever you get a non-zero determinant, you get a non-singular matrix. So this is a kind of quick check whether a given matrix is non-singular without having to get the inverse. Why is this so? So let's see the proof. If A is non-singular, by the way, by a previous theorem, it is a product of elementary matrices. Using the previous corollary, the determinant of A is simply this, the product of that E1, that E2, up to that EK. But remember that each one of these determinant is not zero because each one of these are elementary, is an elementary matrix, so none of these is zero, so the product is not zero. So the determinant of A is not zero. Conversely, if A is singular, now what will happen if A is singular? If A is singular, well, we know that if A is non-singular, the RREF is IN. And if A is singular, the RREF of A is not IN. Meaning, there are fewer than n pivots in the RREF of A. So if you have fewer than n pivots, what can you say about the RREF of A, which is B? This B has to contain a zero row if you wanted to have fewer than n pivots. And therefore, the determinant of B is zero. But B is the RREF of A, meaning B was obtained from A by performing a sequence of elementary row operations. Hence, you can write B as EK times E1 and so on times E1 times A, where each of these are elementary matrices corresponding to the elementary row operations that you have performed. Hence, taking the determinants of both sides, this is 0, magiging ganyan siya, just as stated in the previous corollary, no? But each one of these, no? Each one of these is not 0. Therefore, if the product is 0, kasalanan nyo nung that A because it is 0. Right? So if A is non-singular, then the determinant is not 0. If A is singular, the determinant is 0. Therefore, A is non-singular if and only if its determinant is not 0. So let's calculate the following determinant and determine whether it is non-singular or not. So this is a 4x4 matrix, so obviously the basket weave method does not work here. So what we do instead is we try to apply elementary row operations in order to transform this into an upper triangular matrix, because an upper triangular matrix has a very simple determinant. For example, we need a pivot over here on the 1, 1, and 3 to start with, but we do not have, no? What you can do is to look for other ones, no? In either in this we can use this one or this one by simply using a row swap or a column swap. So let's just do a row swap. But by doing a row swap, take note that you are introducing a minus sign. Okay? E1 minus 2, negative 5, negative 7, negative 3, 9, 5, 4, 2, 1. Okay? Now that we have a pivot over here, we're going to eliminate everything under it using type 3 operations. Take note that by doing type 3 operations, we're not really doing anything to the determinant, so we are safe. No need to record. Okay? So let me do the elimination for you. So here, so I hope my computations are correct. So take note here that I did 3 type 3 operations. Next is to construct a pivot on the second row. So here we wanted to get a pivot, but that's a 7, and I don't get to have anyone from here, no? Any one. No, I mean one. So I cannot just use row swap. So don't move the first row anymore because that's already fixed there. So instead, I wanted to think of the second row as if each factor has an extra factor of 7, right? I'm going to factor out that 7 over here. So it will be something like this. 0, 1, 3 over 7, negative 10 over 7. Okay? And then just copy each of these. Minus 8, 29, 0, 14, 7, negative 19. So what we do now is, from here, we simply eliminate the two that are below the ones. Okay? So we use the following. So let me do the calculation again for you. Okay, there you go. I've endured this calculation and I get the following as a result for the next step. Next, I wanted to have a pivot on the third row, so maybe I could just switch the third and the fourth rows. Now, by doing that, I am just erasing the minus sign over here. So that's 7, 1, minus 2, minus 1, 4, 0, 1, 3 over 7, negative 10 over 7. So this is a funny matrix, really, because it has a lot of fractions. But sometimes you have to endure all of this in order to get the answer. Now next, we have a pivot over here, and then we have to eliminate that. So what are you going to do? Well, we perform what? What we perform? Okay. We just perform a type 3 operation. We multiply, we replace the fourth row by 5 over 7, by the sum of fourth row plus 5 over 7 times the third row. Okay, so let me do the calculation for you once again. Okay, so this is the resulting matrix upon doing the elimination. So as you can see now, the matrix is now upper triangular. So the determinant will just be the product of the main diagonal entries, but most of them are ones. So the determinant is just 7 times 1 times 1 times 1 times 38 over 7. So all in all, the determinant is 38. Okay, so what is a good way to check if your answer is correct? Well, maybe you can use the Scilab once again or GeoGebra, whatever. Use the determinant function of these softwares. So let me switch to the Scilab mode. Yeah, so I think 38 is the correct answer. So let me leave this to you as an exercise so we don't have to spend more time. For what values of A, B, and C is this non-singular? So maybe you can work on this, or maybe on the live session we can work on this example. So to do this, by basically you just compute the determinant of A and determine when is this not zero. When is the determinant not zero? The following theorem, in general, now if the determinant function is multiplicative, when you say multiplicative, the determinant of the product is the product of the determinants. So, why is that the case? Well, we consider two cases. First case is when A is non-singular. Second case is when A is singular. If A is non-singular, then again, A is a product of elementary matrices E1 up to EK. So I can write AB as follows, right? But the determinant of this by the previous corollary is equal to this determinant, okay? But this product is just A. So that's why that's that A times that B. On the other hand, the second case, if A is singular, then we first claim that AB is singular. You know, suppose for the sake of contradiction, suppose that AB is non-singular, what will happen? Then it's going to have an inverse, right? Because AB is non-singular by this supposition, and write it as you have an inverse for AB. So when you multiply AB with the inverse of AB, you get IM. But as you can see over here, A, when it's multiplied to this matrix, gets the identity as well. This will imply that A is non-singular because it has its own inverse, which is a contradiction to the fact that A is singular. Therefore, the product AB is singular. And therefore, its determinant is 0. But 0 can also be written as 0 times that B. And because A is singular, that A is also 0. So even when A is singular, the equation actually holds. And as a corollary to this, if A is non-singular, we get to have the determinant of its inverse. It turned out that the determinant of the inverse is the reciprocal of the determinant of A. Why is that so? It must come from this equation because if A is non-singular, this is equal to the identity. Taking the determinant of both sides, because the determinant is multiplicative, you have the following equation. But the determinant of In is 1, and the determinant of A is not 0, so I can divide both sides by that A. Now, take note that dividing both sides is now legal because these are now all just scalars. These are not matrices anymore. So the determinant of A inverse is the reciprocal of the determinant of A as shown in the following corollary. As an example, if the determinant of A is 38, we know that it's non-singular because the determinant is a non-zero one. Therefore, the determinant of its inverse, even though we don't know what the inverse is, has to be 1 over 38. Alright? So from here, we will continue our discussion on determinants next meeting, and I will be introducing a new method of calculating determinant, which uses the cofactor expansion or the Laplace expansion. And as a corollary or consequence to that, we will be having the Cramer's rule for solving linear systems. Alright, I hope to see you in the next live session or video lesson. Thank you for listening.